Dear friends, today through this e-content, we are going to discuss about natural frequency of sound. First of all, let's learn what a simple pendulum is. A simple pendulum is an arrangement or device where a point mass is attached to light string and suspended from a fixed support, just like in this picture. If we slightly move this point mass to one side from its mean position, that is the point O in this picture, and release it, we can see this point mass moving to each side, just like the motion of a swing. This to and fro motion of pendulum is known as oscillation. Now let's see this once again.
Simple pendulum. A simple pendulum consists of a metal bob suspended by a light inextensible string from a fixed point. Let us now get familiar with the terms that we come across while learning a simple pendulum. The length of a simple pendulum is the distance from the point of suspension to the center of gravity of the bob. The resting position B of the pendulum is known as the mean position. One complete to and fro movement of a pendulum about its mean position is known as an oscillation or vibration.
The number of oscillations made by the simple pendulum in 1 second is its frequency or time period. The unit of frequency is known as hertz. We can calculate the frequency of a simple pendulum by using the equation frequency f is equal to number of oscillations n divided by time t. Now let's see what happens to the frequency if we change the length of the pendulum.
Here we have a pendulum and a stop clock. Now we will count the time it takes to complete 10 oscillations. Swing the bob to one side and leave it. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Oscillation is a motion that repeats itself regularly, so it took 13 seconds to complete 10 oscillations. So the time period for the pendulum is 1.3 seconds per oscillation. Now we have shortened the length of the pendulum. We will see the effect on the time period. Let's swing the pendulum and start the stop clock. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now it took 8.5 seconds to complete 10 oscillations. So the time period for the shorter pendulum is 0.85 seconds per oscillation. Hence we note that the time period of a pendulum depends on the length of the pendulum.
As the length of the pendulum increases, the frequency decreases. Now let's consider a scenario. If we fix one end of a hacksaw blade on a table and set the free end into vibration, it's evident that the frequency of vibration of hacksaw blade is greater than the frequency of simple pendulum. We can hear a small sound from the vibration of hacksaw blade. The sound produced by simple pendulum cannot be heard because the frequency is very low. But on vibrating hacksaw blade, its frequency being very high, the sound can be heard. There occurs a difference in sound in accordance with increase in frequency. Now let's take another example. Set different tuning forks of different frequencies into vibration and listen to the sounds produced. Notice the frequency marked on each of them. We can experience the difference in sound produced by them. The tuning forks of different frequencies produce different sounds. These are all due to a property known as natural frequency. Natural frequency. When a body is set into vibration, it vibrates with a particular frequency of its own. This frequency is its natural frequency. The difference in the sound produced from the simple pendulum, hacksaw blade, and the tuning forks are all due to the difference in natural frequency. Now let's see what are the factors that influence the natural frequency. The first factor is nature of substance. In these pictures, we can see PVC pipes and metal pipes. If we make instruments using PVC pipes instead of metal pipes and try to produce sound, we can hear the difference in sound. Even if we take a PVC pipe in the exact same length as the metal pipe, the sound produced are different. As the nature of body changes, natural frequency changes and sound changes. The next factor is length. We learned that as the length of the simple pendulum increases, its frequency decreases. We use at home instruments made of metal pipes for producing sound and for decorative purposes. Do all pipes make sounds of same kind? No. The sound changes as the length of the pipe changes. So, length is another factor which influences the natural frequency of an object. The next factor is tension. If we stretch a rubber band with two pencils and set the rubber band into vibration and listen to the sound, and then again listen to the sound by changing the tension of rubber band, there will be a difference in sound we listen to. As the tension changes, the natural frequency of the body changes. The next factor which influences the natural frequency is area. Fixed diaphragms made of balloons of the same tension on one end of two pipes of different diameters. Beat them evenly with the thin midrib of a coconut leaf. There is a difference in sound produced. As the area changed, the natural frequency of the body changed, and thus the sound produced are different. Now let's look into the another factor which influence natural frequency. That is area of cross section. If we stretch two copper wires of same length and of different thickness under the same tension and try to make sounds by plucking them, we will experience a difference in sounds produced. Here, the difference in area of cross section caused the change in sound produced. It is another factor which influences natural frequency of a body. So today we have learned what is a natural frequency, what is a simple pendulum, and the factors which influence natural frequency of a body. Hope you all understood. Thank you very much for listening.